Every set of ordered pairs is a relation, but every relation is not a function. We have a diagram showing that relations cover more ground than functions. Functions are a subset of relations. A function is a relation that is one-to-one or many-to-one. Here we see 1x to 1y and many x's to 1y. One method for determining if a relation is a function is the algebraic method. In the algebraic method, you say to yourself, well, for every input of x, how many y's am I going to get out? For example, if I put an input of 2, I'll get 2 squared, which is 4. So an input of 1x gives me 1y. So this is a function. If I put in input of 4 here, I get plus or minus the square root of 4, which is plus or minus 2. So for every x, I get 2 output values for y. So this is not a function. Alternatively, you could do it graphically. If the relation passes a vertical line test, it's a function. What's the vertical line test? A vertical line drawn anywhere on the graph should only hit the graph in one spot. You can see this is the graph of y equals x squared. It does pass the vertical line test, whereas y equals plus or minus the square root of x does not, because a line drawn here would hit the graph in 1, 2 spots, whereas a line drawn in any place here only hits my graph in one spot. A function f, or a mapping of f, from a set capital X to a set capital Y is a relation that assigns to each element x in the set capital X a unique element y in the set y. That's what we've been talking about before. X, the capital X, is the domain, and y is the codomain, or you've seen it as range before. The element y is the image of x under f, and it's denoted f of x. Another word for y is f of x. And x stays x. Sometimes you see it as a mapping. The function is mapped from x to f of x. With this diagram, we can show the mapping of x onto y, where f of x is a rule in terms of x. You have inputs here, which are your x's, and they map onto y's. Following this rule, you do something to the x's. Maybe you square and then add 1, for example. The range, you see, is a subset of what we call the codomain, the possible y's. Hybrid functions are composed of relations that consist of more than one function, where each function is defined over mutually exclusive domains, where we remember that mutually exclusive means one or the other. We can have f of x is defined as g1 of x when x is an element of x1, and g2 of x when x is an element of x2, provided that x1 and x2, or the intersection, is the null set, meaning they're mutually exclusive. They don't overlap. Here's an example of a hybrid function. F of x equals x when x is greater than 0, and f of x equals x squared when x is less than or equal to 0. You see that their domains do not overlap. They're mutually exclusive. Continuity. A graph is said to be continuous over domain if it can be drawn without lifting the pen from the paper in that domain. In other words, there are no breaks. We'll be looking at 3 types of discontinuity. Our first one is jump discontinuous. Our graph comes down to x equals a and then jumps down here and keeps on going. Notice our value at x equals a is there. We have an open spot down low. Here we have asymptotic discontinuity. As I approach the asymptote at x equals a from the left side, I'm going towards infinity. My f of x value goes towards infinity. And if I approach it from the right side to the left, I'm going to be going towards negative infinity. So I definitely have asymptotic discontinuity. I have to pick up my pen. Lastly, we have missing point discontinuity for obvious reasons. The absolute value function, y equals the absolute value of x, is the same as y equals the square root of x squared, which requires us to take x if x is greater than or equal to 0, and negative x if x is less than 0. If it's positive, keep it positive. If it's negative, make it positive by taking the opposite of it. Notice if I'm drawing a graph, if I just draw y equals x and I continue it down like this, the absolute value function will reflect any part of my graph that's below the x-axis above the x-axis. When we're graphing y equals the absolute value of some function, first you sketch y equals f of x. For example, here's my sketch of y equals f of x. And then you reflect about the x-axis, whatever parts of the original graph lie below the x-axis. So from here to here, we lie below the x-axis. flip it over or reflect it over the x-axis and it looks like that. There's your original function, and there is now your absolute value function. When graphing y equals f of the absolute value of x, notice the absolute value sign is just around the x now. You replace the part of the graph of f of x for x is less than or equal to 0 with the mirror image across the y-axis of the part of f of x that lies in the domain greater or equal to 0. For example, if this is our line and we want to graph y equals f of the absolute value of x, well, we just take up to this line here, y equals 0 line, or x equals 0 line, it's the y-axis, and we take the mirror image of whatever's in the positive x domain. We're going to take the mirror image of that. Don't get confused between this and absolute value. It's just that I picked a straight line. I could have drawn that as a curvy line. For this particular type of function, whatever's to the right will get flipped over to the left.